Hi, my name is Jim, and we'll start by discussing some forces that account for what happens in an electrical circuit. And the first force we're going to talk about is an electrostatic force, and the symbol for this is a script E. Now this in a branch of physics goes quite deep, and we're not going to go deep at all. What we want to do is get our foot in the door for understanding electric circuits. So I'm going to start here with a voltage source, and this is the symbol for a voltage source. We have a positive and negative terminal, and next to it's my attempt to draw a car battery, so we have a reference, and the magnitude of that source is 12 volts. Here we have wires connecting our circuit here, and I want you to consider this to be two pieces of aluminum foil, say 1 foot by 1 foot, with a piece of glass in between them. And well, what the glass does is it serves as an insulator, and if we didn't have that glass, air would also be an insulator. So when we apply the 12 volts to this, we have an electron current that flows in this direction and charges the bottom piece of aluminum foil, and likewise then repels electrons back into the source of the battery. Now that in itself isn't too exciting, although this device is called a capacitor, and in later application it is just super useful. But let's see what's going on inside of this. So here we have our two plates, and I've not shown the glass inside of it, and the field it sets up because of the difference in electrons, where after the circuit's closed we have an abundance of electrons here and a few missing at the top. So it's not evenly distributed between both of these plates. So the force I'm referring to, electrostatic force, indicates lines of force, and they start at the positive side of this capacitor and go to the negative side. So fewer electrons represent a positive charge, and many electrons represent a negative charge in this particular example. So if we break this down into a very simple model using say a positive charge and a negative charge, is what we see is the electrostatic force lines go from the positive to the negative charge. So what we can conclude from this, and kind of important here, we'll see this coming up, is like charges repel each other and unlike charges attract each other. And this may sound exactly like a bar magnet or magnetic field, and that is exactly true. So if we have unlike charges attracting each other, why then in a battery doesn't the excess of electrons on the negative terminal just flow backward through the battery to the positive terminal? Pretty good question. And the answer to that is that batteries store chemical energy, not electrical energy, and it's that chemical energy that allows an abundance of electrons to be here, fewer electrons here, and hence that represents an energy source. So a source is a body of energy that can be used in an electric circuit. Many people think that batteries store electrical energy. They do not. This stores electrical energy, but that's a topic for another conversation. So we have electrostatic force, and it has a cousin, which is electromagnetic force, and the variable for this is a script H, and it can be represented very simply by what I think everybody's familiar with would be bar magnets. And like electrostatic charges, like poles repel and unlike poles retract. So if we were to look at an electromagnetic or magnetic flux, if you will, lines of force, if we have two north poles here, we see that they are in fact repelling, and we would realize that force by pushing apart. And if we have a difference, a north and a south pole, then we feel attraction, and the magnets want to pull itself together. Now, in magnetics, this is very easy to see. You have a magnet, and that's the way it behaves. Well, it's similar to an electrostatic field, too. Now, in this circuit here, I have a positive charge on this plate and a positive charge on this plate, and the force of this tends to want to push the plates apart. Now this is harder to visualize because we don't work with this typically in our lives. And likewise, if I have more electrons on this plate, fewer electrons on this plate, they tend to attract. So the same principle holds forth for magnetic and electrostatic fields. Now realistically, that's all very nice. What good is it? And I guess tour de force explanation is that radio waves are made up of electromagnetic and electrostatic fields that move through space. And when they come across a wire called an antenna, these two fields shuffle electrons around, and that becomes the signal which ultimately, say, our cell phone can pick up from a cell tower. So what we're talking about here is a very, very mild introduction to a horrifically useful set of physics which makes our lives easy. Now, let's look at electron flow, and that's kind of what electricity is all about, so I guess that would be a pretty good thing to talk about here. We have two basic types of materials in this. One is called a conductor, which conducts electricity. It's kind of like a pipe which conducts water, and the other is an insulator, which absolutely does not conduct electricity unless certain conditions are made, bad conditions, which are called breakdown. So this offers little resistance to the flow of electrons, some resistance, yes, and we're not discussing superconductivity, and insulators offer a lot of resistance to the flow of electrons. Now, if we take a look at the Rutherford Bohr model of an atom, and when I use the word model here, what that means is it's a simplified version of what's usually a complicated arrangement. For example, a transistor is horrifically complicated, but yet it can be represented by a model with maybe 4 or 5 electronic parts that reasonably mimics the way a transistor works over a lot of different circuit configurations. So we use the model instead of a math-intensive array of calculations to determine how a circuit works with a transistor in it. Likewise, the Rutherford Bohr model uses the model of the solar system. We have the sun and the planets orbit around it. And that's kind of what we're saying here, is that the sun would be represented by the nucleus, and the planets that orbit it would be represented by electrons. So that's kind of an easy concept for us to pick up because we're somewhat familiar with the solar system. Now, the nucleus has two general types of particles in it. One is the proton, indicated here in black, and protons have a net positive charge of 1. We also have neutrons, indicated as blue circles here, and the purpose of a neutron, which has no charge, is to stop the protons from flying apart. Now, protons have +1 charge, as we can see, but like charges repel. So it's the mission of a neutron to stop that from happening. So as atoms get more and more complicated, as we move up toward uranium, the proton to neutron ratio, or let me say that backward, the neutron to proton ratio increases because there's more neutrons required so that the nucleus does not fly apart. In uranium, it's on the verge. If the nucleus is hit by a slow-moving neutron, it splits, forms different elements, and in the splitting process releases a lot of energy. So here we have our electrons here, and I'm showing these kind of in a haphazard way right now, but whatever. And these are in what's called orbitals. So the Earth is in an orbital, and so are electrons, and this orbital here is closer to the nucleus. That would be like Mercury, and these orbitals would be outer planets, we'll say, the Earth, and perhaps Mars, and so on and so forth. And we're showing them simply spinning around the nucleus. Is this the way it really happens? No way. Is it complicated? Very. But this kind of gives us a starting point. So in this model here, we've got a relatively simple understanding of what's going to be going on here for the purpose of understanding the conduction of electricity through a circuit. So what we're interested in here is what's called the outer shell electron, and shells are locations where electrons orbit, and these locations we can consider to be as how far away they are from the nucleus. So the outer shell electron is kind of the last one, and this is the one we're going to be looking at when we define insulators and conductors. So in this, all the inner shell electrons are shown by these black dots and whatever. Not drawing them, I just want to concentrate on the outer shell electron. And what we see in an insulator, and I'm showing 8 electrons in this, and that's indicative of a stable atom, is that they're very tightly bound to the nucleus. It's kind of like Mercury. It's close to the gravitational attraction of the Sun versus, say, Neptune, far, far away, or Pluto Charon, which is even further away, is less bound to the Sun. So if we wanted to break free one of these electrons to conduct in our circuit, we would have to apply an awful lot of force to move this guy out of this orbit and hop over into the next atom, and that's basically what happens is electrons hop from atom to atom as they move through the circuit. So it's a strong attraction which makes this a good insulator, and different materials of a given thickness have different breakdown voltages. Some insulators are better than others. Now on the other hand, a conductor, I'm showing this is one electron in the outer orbital, which is typical, is very loosely bound. So if we apply a voltage across this, this electron would not take much energy at all to hop over to the next guy, and the one here to your left would then come and fill this. So conductor is not much energy all is needed, and in the insulators a whole lot of energy is needed to free up an electron to conduct electricity. So we look here at a wire, and let's not think about this ink here that's connecting them together right now. We see that the negative side of the battery is connected to this side of the wire, and positive side of this, and this puts a pressure across the wire, and that's the electrostatic pressure. And what happens now is the nucleus is the little black dots, and the electrons are, my indication is the blue arrows, tend to hop from atom to atom, and when this is vacated, a new electron will enter from the negative terminal of the battery, and over here an electron will leave the wire and enter the positive terminal of the battery. So that's kind of electron drift, and it is from negative to positive in what we'll call a load. And load is a piece of wire in this case, but it has a lot more meaning later. So as you can see this is what causes electrons to flow, and when we do this, when we extract an electron here, put one in over here, what we use is a small amount of chemical energy to do that. And if we do it long enough, what will happen is that the source here, our battery, if you will, or our cell, will become discharged. Now, in a lot of cases, what we do is we take the battery, it's depleted of chemical energy, and we throw it out. In other cases, like rechargeable batteries, car batteries, lithium-ion batteries inside your cell phone, if we reverse the voltage across it, we can restore the chemical energy inside the battery. That is, electrical energy goes in and chemical energy results from that. In this case, we have chemical energy within and electrical energy is expended in our external circuit. So, in the process of forcing these electrons to hop around in here, even though it's a good conductor, what happens is that energy has to be accounted for, and that is dissipated in the form of heat. So in every wire in your house which is drawing some kind of current, say a light circuit, the wires in the wall are slightly warm. Now, if the wires are sized correctly, it's no problem. If they're not sized correctly, well, you can burn your house down. So if we look at this, and this is kind of an expanded view of this, and what we're going to kind of do here is explain this here hopping around of electrons, is to think about the Bohr model of the electron being in an orbit, and as we apply energy to it, and that would be the electrostatic field and subsequent flow of electrons, what will happen is we add energy to the electron, and it moves from what's called the valence band into the conduction band. And when it's in the conduction band, it simply has more energy and can move. So valence means that it's in orbit, and conduction band means that it's free to move through the material. So the question then is, well, how much energy does it take to get an electron from the valence band into the conduction band? And this is not only going to determine if it's an insulator or a conductor, but if it's a good conductor or a fair conductor. So we're going to look here at what's called an energy diagram, and the valence band is shown here as being a lower energy, and the conduction band is a higher energy, and this would be representative of an insulator. So if we want to move an electron from this band to this band, we have to apply a lot of energy to do it. On the other hand, for a conductor like copper or silver, which is considered to be the best conductor, is that the valence band and conduction bands overlap. So it takes very little energy to free up an electron. Now, if we take a look at this, let's consider silver for a minute in a mirror. If we look at a mirror, what we see is an image in it. And it's shiny. And the reason that's shiny is that in silver, these electrons are so loosely bound that the very heat of the room causes them to be in the conduction band and able to move. So that's why it's shiny. And copper is shiny also to a lesser extent if we polish it, because it gets oxides on it, and the same with silver. Oxides are interaction with oxygen, and the only known oxide to conduct electricity is silver oxide, and that's the darkness people see on their silver spoons and forks and so forth. Copper oxide is a very, very good insulator. So what we have here now, if we take a look at our mirror again, is a light particle called a photon, which is a particle and a wave, or a wave and a particle, don't ask, strikes a silver atom, moves the electron to a higher energy level, it stays there for a little bit, then decays. Now energy has to be accounted for, and when it decays, it emits the same amount of energy that it absorbed. And that energy is a photon which comes out of the glass back to us. So that's kind of the way that works, is absorb energy, go up, stay there for a little bit, drop back down, re-emit the photon back toward the source. So while I'm here, electrons also are particles and waves, or waves and particles. And things get complicated very quickly. So that's our energy diagram here, and I think it fairly well explains the difference between a conductor and an insulator. And just kind of put this into perspective, this is a prototype I'm working on, and the green you see here is a circuit board. It's epoxy glass, and it's a really good insulator. And then the actual wiring, as you see over here, is made of conductors, of course. This here is a piece of copper stained glass tape. You put around stained glass and then you solder them together. And it's the ground, and that has to be a really, really good ground, that is to say low resistance in this particular circuit, or bad things happen. So that's a combination of the insulator, and what the insulator's purpose is to keep these wires from having electricity flow between them. Because if it did, well, this wouldn't work too well. So that's kind of an example, I suppose, a hands-on example. The insulation on a wire, say a lamp cord. The wire inside the conductor, and the rubberish plastic on the outside is the insulator. And what's really bad is if that becomes worn and the two conductors touch each other, say in a lamp cord, because that represents a short circuit. Big spark, lots of heat, possible fire, and so forth. Now, how good can an insulator be? So here we're going to take our two plates again and our piece of glass, and we're going to apply a voltage across it. Now, when you see a source like this with an arrow through it, what it means is that's variable. It's a variable voltage source. And if we increase this high enough, is we are going to rip electrons out of the glass, which are tightly bound because it's a good insulator, and they then will conduct. Electricity will go from, electrons will go from this plate to this plate through the glass, and that's called breakdown. And when that happens is you typically have a high voltage to break it down, and that's relative. High current, and the product of the two, as we'll see later, is high power, and that's dissipated as heat. And realistically, most of the times breakdown is catastrophic. The circuit will no longer work. There are exceptions to that. Some devices work in the breakdown mode, but we won't concern ourselves with that at the present time. So hopefully what we've covered here presents a good understanding of the basic materials having to do with how we make an electric circuit, which we haven't defined yet. And should give you a pretty good idea of the background of what's going on. Now, of course, we've got a lot of laws and so forth in electronics that sit on top of this that govern how this behaves, and we'll be working into these in the coming future. So that'll conclude. Thank you for watching, and this will be followed by a few animations showing electron orbitals and current flow and so forth.
Here we have an animation using Rutherford's model, and what to note is that we have a nucleus in the center, inner shell electrons which are tightly bonded, and an outer shell electron. It's a single electron, and it would take very little energy to move this through the circuit. Another animation of nucleus with electron orbitals. In this case, the nucleus is spinning. In this animation, we see the difference between a large and a small current flowing through a conductor with a given area. And what's interesting to note here, and it's obvious that this is a larger current flow, which would represent the movement of electrons, is if you watch right here exiting the wire, occasionally you'll see one electron and occasionally two. And that random flow of electrons actually produces a type of noise in a circuit. It's called random arrival. Here we can see a relatively interesting picture. We have a copper wire that's inside of an insulating sheath that's sometimes called a jacket, and what we can see here is the nucleus of each electron, and of course there would be billions more of them in any practical wire, and the surrounding orbitals. And basically the outer shell electron, if exposed to an electric field across the wire, would be hopping, say, from this atom to this atom, while its electron might be hopping from this atom to this atom, while this electron would be hopping from this atom, and then finally we would be exiting the wire into some external circuit, say a battery terminal or a connection into a filament or something like that. In this animation we see the outer shell electrons in purple, which are being passed along a wire, and of course there would be many more conductor atoms inside of this. We can consider it to be copper. It could be something else, and the field across the wire would be positive on this side and negative on this side, so the electrons would be repelled by the negative terminal and attracted by the positive terminal.